Complex roots. Hope you're ready for it. This is a little strange. The work's a little tedious, but I think it's quite interesting, especially to understand a little bit more about complex numbers, imaginary numbers. All y'all future engineers, math people, people that just have to take a lot of calculus, things like that, physics. You wanted to have a little bit of a knowledge about these things, so let's dive deep. Let's dive deep. So complex roots, and when I'm talking about a complex root, possibly like, hey, go find me all three answers of the cube root of 1. We're actually going to do that in an example problem. And when complex numbers, the answer is not just 1. That's one of the answers. There's actually 3 answers. There's 3 of them. One's going to be one of the answers, but in complex numbers or imaginary numbers. There's imaginary numbers. There's 2 other imaginary numbers that if you cube them, they equal 1. It's weird. It's weird. So that's what's going to happen. So I'm sparing you the proof as to how this happens, and we're just going to go straight to the theorem for finding nth roots of a complex number. So for a positive integer n, again, you know what I mean? A whole number and it's positive, okay? The complex number in that trig form. That's just that trig form, that complex number. And it says that we have exactly n distinct nth roots given by. Again, meaning like maybe z is just equal to 1 and we want to know the cube root of z. Oh, I mean 1. You know what I mean? So the cube root of z, cube root of 1, and we're going to end up with 3 different freaking answers there. Look at this. We got little indexes, k's, k's, k's throughout this formula. Then there's n's, where k's go from 0 on up to the number right before n. Man, there's a lot going on, but I think the best way of doing this, instead of explaining out the whole formula, is let's just mess around with it and let's dive into a problem. And I think that helps it to become more clear. This is a process more than anything else, knowing where things go, how to define your variables. So let's just get a practice in. So what I have is we would just want to find all third roots of 1. All right, keep talking about it. Find all cube roots of 1. So let's start our problem. The first thing you're going to do is just say z is equal to 1. And we're going to want to know the cube root of it. So z equals 1. We want the cube root of it, or the third root of 1. But the thing we need to do is we need to take just that number 1, and we have to convert it in to our trigonometric form. Right? So we're going to find all third roots of 1. So when I look at this, we're like, well, what's the radius? It's 1. Now what's the angle? Well, just draw it. This is 1 plus 0i. So anytime you just see 1, that means there's no freaking imaginary part to it. So remember how we graph this? This is the real portion. This is the imaginary portion. So what we have is a kind of a point, 1 comma 0. That's 1 comma 0. The x and the y portion. Okay. Okay. Now, as we move through, what is that going to be? What angle is that? Isn't that 0? That angle's at 0. Remember, like 0, pi over 2, pi, we superimpose this thing right on top of it. 0 or 2 pi. So let's plug in 0. That's our angle. Cool. So we can say that z is equal to 1 times cosine of 0 plus I sine of 0. I mean, I'm in radians, not degrees when I use it. So we don't even really need that 1 that's hanging out in front, but I'm just showing you that the radius is there. So now we need to go through and start messing around with this, this process. We have a plus 2 pi k in our problem. which means we're going to have to start with k equals 0 and plug it in, and we're going to get an answer. Then we're going to plug in k equals 1, and we're going to get an answer. And then we're going to plug in k equals 2, and we're going to get some sort of answer. But let's define all of our variables right now. In here, it says if you want to take it to the third root, the nth root. That means that's the number we're going to be dividing by every time. That number doesn't change. Only k changes. N's going to remain the same. Theta's going to remain the same. 2 pi is going to remain the same. It's only the k that's going to change. So let's go find our n. And our n is how many roots. We're going to the third root. We say the third root of z is equal to the radius, just raised to that power, rooted, and then it goes cosine of the angle. Oops, let me make this a little bit better. Make it just a tad bit better. It's the angle theta plus 2 pi, and this is the thing that changes, the k, all over n. All over n, but we already know n. Oops, go away, stupid thingy. Right, that first part right here. That n is going to be 3. And now we need to do the same thing with our plus I sine. And it's going to be the same interior, so you're not going to have to do this twice. And it's going to be our theta plus 2 pi times that k that's going to change. We're going to have to plug in numbers for it over that 3. What's dope is we already know our angle, right? That theta, that's what we found. It's why we had to convert this thing so we know what is our angle. It's 0. So I'm going to cheat and just plug in 0. Okay, that's our general formula. We're going to get all of our solutions from this. Now the game starts off as we're going to plug in k equals 0, k equals 1, k equals 2. We go all the way up to the number right before the root. Right? We're taking a third root, so we do 0, 1, and 2. And if you count on your fingers, 0, 1, 2, that's 3 different numbers, giving us our 3 answers. So let's start off when k is equal to 0. We're going to find that we have, our radius. I'm sorry, I forgot to. We'll do that in this problem. So we're going to take the third root of 1, that's 1, by the way, cosine of 0 plus 2 pi over 3 times 0. So that 2 pi is just going to go away. Not the whole thing. Well, it will, but, and I sine of 0 plus 2 pi. And it's always going to be the same thing in both arguments, okay? It's not going to be different. Times 0. So there's only one calculation. So what do we get? This is going to be equal to 1 times our cosine of, and the 0 times 2 pi just goes away, giving us 0 over 3, which is equal to 0, plus I sine of, we're going to get the same thing. There's no need to even look at what's on the right-hand side. Isn't that the same as z? You get 1 times 1 plus 0i, right? Sine of 0 is equal to 0, cosine of 0 is equal to 1. Got to have that down. So since there's no i's, this is just equal to 1. But we already knew that, didn't we? Didn't we know the cube root of 1 is equal to 1? That's the one real answer we're going to get. We're going to get 2 complex numbers as well. So that's the real one. You should expect that. That happens a lot. You end up just getting some, especially if you're taking roots on 1. One of the answers has to be freaking 1. Surprise, surprise. But now we need to move on to k equals 1 and k equals 2. There's our first. So now let's look at k is equal to 1. So we rewrite it. Now I'm not going to write it in as, oops, I don't need an equal sign here. The cube root of 1 anymore. Come on. Even the fact I'm writing 1 is silly. So we have 0 plus our 2 pi over 3, and then we punch in our number, times 1. Plus I sine. Same thing. 0 plus our 2 pi times 1 over 3. And let me There we go. That one proper. And let's evaluate it. This is equal to, I'm losing that 1 because that's silly. 1 times 2 pi is 2 pi. 2 pi plus 0 is 2 pi, so we get cosine of 2 pi over 3. Now, there's no need to even look at the other one. It's going to be the same dang thing. There's not 2 calculations. There's 1. We just have to write it twice. And now, evaluate it. Cosine of 2 pi over 3 is equal to negative 1/2. Sine of 2 pi over 3 is equal to positive root 3 over 2. And I'm going to put my I right there, making it very distinct that you can see it's not underneath that root, and that's why sometimes it's written in a strange spot, just to make certain that we know that's not an issue. All right. This is a long one, huh? Almost done. So there's an answer. If you were to take that and cube it on up by using Demoivre's theorem, you would find out that the answer is equal to 1 by using Demoivre's. That would be a fun problem. Make you find a root and then use Demoivre's to prove it at the end. That'd be interesting for a problem. I could test both things all in one shot. And you'd have to know what the heck you're talking about. I like it. All right, now let's do k equals 2. I know this video is going long. I should just shut up. So we have that 1 times our cosine of 0 plus 2 pi over 3, but we got to multiply it now not by 1 but by 2. Plus I sine of 0 plus that 2 pi all over the 3, and we're going to multiply by 2, which is going to be, what is this? This is equal to cosine of 2 times 2 pi is equal to 4 pi, and then we're adding 0 and dividing by 3. There it is, cosine of 4 pi over 3 plus I sine of 4 pi over 3. Now let's put that thing into standard form so we can figure out what the heck our last root of unity, by the way, another way of saying it. You might hear roots of unity. And this is going to end up just being a negative root 3 over 2 at the end. So negative 1/2 minus root 3 over 2i. And there, my friends, is 1, 2, and 3 answers. I'll have another long video for you showing you just another kind of version of it. And I think you got about 5 problems in your homework, so I'll give you one more, and I think it pretty much exhausts all the different possibilities you may see. I know this is long and tedious. I know it's a tough process, but get your practice with it. You got 5 in your homework. You got these to look through. If you have questions, please ask in class. I always got your back. See you.